Welcome back. Just as I was about to start recording this video, I realized I did not put any kind of memes in any one of my notes, and I'm a little disappointed in myself. I thought for sure I would have a Baby Yoda thrown in somewhere in there, just a little hidden peeking out at you, but I totally forgot. So I want to apologize. So before we get to rational functions, I had to bring that up because it was bugging me. Okay, well, this section, the title really doesn't even say anything of what you're doing. Rational functions is just, it's like a whole chapter. The I can statement says a little bit more of what we're actually working with. So in this section, by the time you're done with 8.4, you'll want to be able to identify any kind of transformations that are made to the rational function y equals 1 over x, and it specifically has to be 1 over x. That's the only rational function you'll need to know how to transform, because there's a lot of rational functions, but 1 over x is the only one you'll actually have to know transformations on. And you'll want to be able to identify all sorts of different information from the different functions. So, heading into that. I'm sure some of you have zero interest in printing out your notes. And, well, this might be a section you'd want to if you normally don't. But you can always open them up and look at them on the Chromebook or computer, so it's your choice. But this section, there's a lot of information that we got to cover, so it's not like the other ones where we usually do examples together. And I see that my poorly drawn graph over here, the XY axis, I absolutely forgot to include a drawing of 1 over x. So when we did inverse variation in section 1, we actually had drawings of 1 over x, because 1 over x is the most basic inverse variation, and it's called a hyperbola. So you basically have two different curves in opposite corners. You know what? That's actually a lot better than I expected that would come out. This is pretty much the drawing of y equals 1 over x. And so all the transformations we make would come off of this drawing. Well, the transformations are the same as what we've done throughout the year. It looks slightly different in the problem because there's no parentheses, there's no squared. So the first thing is the positive and negative. So if your fraction is positive, there won't be a sign anywhere. You don't write a plus sign. But that would mean it's right side up, so that's the normal one. But if there is a negative sign on the top of the fraction or in the front of the fraction, that would make it upside down. And so essentially an upside down fraction would have the curves in the opposite corners. And then there is the multiplier on the top. The normal parent function has a 1 up on the top of the fraction. Your transformed function could have different numbers. So that's the vertical multiplier. So if there's a 3 on the top, well then technically every point is 3 times further away. So it's called a vertical multiplier. If the number is smaller than 1, like a half. So if your number is between 0 and 1, that actually squishes it or shrinks it. There's different terms. But the top number is called a vertical multiplier. And then the third piece of information you look at is the numbers that are added or subtracted on the x. Now, just like when it was on a parentheses, the numbers that are added and subtracted directly on the x move it left and right. And it's the opposite of what it seems. So plus b would move to the left, minus b to the right. And then the very last piece of information on the end works the exact same as all the others. The plus and minus c moves it up and down. And then these two are actually called translations. So that's the correct term that you'll run into occasionally here. But these are the exact same transformations we've had in the past. So that's why I'm not really going to spend a ton of time talking about them. Now, there is some information that you'll be asked to know from transformations. So you might be asked about vertical asymptotes. Well, on the parent function here, this poorly drawn graph, there is a vertical asymptote at x equals 0. And that's because you can't plug 0 in place of x in 1 over x, because you get 1 over 0. So that's called a vertical asymptote. And the vertical asymptote will always happen at the exact opposite location of the b. So if your function has x plus b written in it, then your vertical asymptote would happen at negative b. If your function has x minus b written in it, then the vertical asymptote would happen at positive b. Horizontal asymptotes, that's the second piece of information. And if I look at my parent function, it does have a horizontal asymptote right there. So a horizontal asymptote is an imaginary line that your graph flattens out at. And whether you're coming from the bottom or the top, it does flatten out at y equals 0. And so a horizontal asymptote would be affected by the plus and minus c, the vertical translations. And it follows exactly what the c says. So if your equation has plus c written in it, your horizontal asymptote would be at positive c. If your equation has minus c at the end of your equation, then your horizontal asymptote would be at negative c. Domain and range. Your domain, I don't know if this is a great way to say this. Your domain and your vertical asymptotes are tied together. Domain represents every location that you can put a number in place of x. So the only place you can't put an x is at a vertical asymptote. So your domain is the exact opposite of vertical asymptotes. So if, for example, you have a vertical asymptote at x equals 2, your domain is everywhere else except for 2. So in this example, we've got negative infinity to 2 along with 2 to infinity. You'll notice that 2 is the only place that it does not exist at. And range, the last thing, is everywhere but the horizontal asymptote. So if your horizontal asymptote is at y equals 3, then your range goes everywhere up and down except at 3. So a lot of this information is tied together, which is what can make it confusing. So absolutely, if you can, write this down somewhere or have it printed out or whatever, but have this information, with you so you can reference it. And this is only half of the info. Here's the other half. Now, the last slide only applied to transformations. And transformations only applied to the parent function 1 over x. Well, there's lots of different rational functions that can look like whatever. As long as you have a top and a bottom of a fraction, you've got a rational function. And there's going to be 4 pieces of information that you're going to be asked to find from any rational function, no matter which one. And it helps if you do them in a certain order. So, first thing that you're going to want to look for are holes. So if you remember what a hole is, a hole, on a graph, obviously, it looks like a hole. But where a hole happens is if you have a factor on the numerator and the denominator that cancels, that's going to be your hole. So the example I guess I'll say is if you have a fraction and you've got something on top times x plus 2, and your denominator has x plus 2 and something else. Well, that x plus 2 would cancel. And then your function would have a hole, your function would have a hole at x equals negative 2. So that's how holes work. Next thing you look for are vertical asymptotes. Now, a vertical asymptote is actually not super far away from a hole. Vertical asymptotes are any factors of the denominator. So let's pretend we have a factor or a fraction that has x minus 1 and x, oh god, I forgot to write the 1, and x plus 3 in the denominator. Okay? This function would have vertical asymptotes at x equals 1 and a vertical asymptote at x equals -3. Now this is exactly why you had to look for holes first, because a hole is only a factor that cancels from top and bottom. Vertical asymptote, you only look at the bottom. So if you don't try to cancel any factors before you look for vertical asymptotes, you might accidentally mistake a hole as a vertical asymptote, when in fact the hole should cancel out. A horizontal asymptote can be found by two different, I don't know, no, let me rephrase that. Rational functions, like I tried to say before, can look all sorts of different ways. We technically are only going to look for horizontal asymptotes on two of the situations. So they all focus on the degree. Okay? So if the degree of the denominator is greater than the numerator, now if you want me to write an example of that, if I have x plus 3 over x squared minus 4x plus 2, the degree of the top is 1, because x to the first is the highest power. The degree of the bottom, denominator, is 2, because x squared is the highest power. So in this case, the degree of the denominator is greater than the numerator, which I know writing it the correct way can be confusing. Well, either way, if the power on the bottom is bigger, your horizontal asymptote is 0. And that's going to be the important thing on this one. If the degree on the bottom is bigger, horizontal asymptote is 0. Second situation, that was first situation. Second situation is if the degree of the top and the bottom are the same. So if I write an example of that one, if I have 2x squared minus 3x plus 1 over 5x squared plus 8, the degree of the top is 2, because the highest power is squared. The degree of the bottom is also 2, because the highest power is squared. Well, the horizontal asymptote is going to be the leading coefficient of the numerator divided by leading coefficient of the denominator. So on this example that I wrote, the leading coefficient is 2 and 5. So my horizontal asymptote would be a y equals 2 over 5. And it's really easy to do once you understand what you're looking for, but absolutely it's a lot of information. I mean, there's no work to do, you just have to know what to look for. And then the last thing to find, the fourth topic, are the zeros. Zeros are also called x-intercepts or roots, it's different things. Well, the way you find those is you make your equation equal to 0 and solve that. I mean, your equation could look like anything, so just make your equation equal to 0 and find the answers. Okay, so that was a lot of information. Let's do a couple examples together, just show you how you're going to use it. So, example 1. Describe any transformations of g of x equal to -1 over x plus 3 minus 4. Well, parent function is 1 over x. So I notice that this negative symbol is a transformation. I notice the plus 3 is, and the minus 4. Those are all different than 1 over x. So one transformation is it is upside down. Now, upside down isn't a very good term, and I should stop saying it as much as I do. It's easy to understand upside down, but a better way to say it would be a reflection on the x-axis, because that's what upside down actually means in math terms. The next change is plus 3 on the denominator, which is the plus 3 on the x. So that is a horizontal translation 3 to the left. A minus 4 at the very end is a vertical translation, because that means it's going to go down 4. So a vertical translation 4 down. Those would be transformations. And there's similar transformations we've done all year. Okay, question 2. Find asymptotes, domain, and range of h of x equal 2 over x minus 2 minus 8. Okay, now this one is still a transformation question because I noticed that this is kind of like transformation form. Okay, so vertical asymptotes. Regular parent function has a vertical asymptote of x equals 0. Minus 2 moves it 2 to the right, so my vertical asymptote is x equals 2. Horizontal asymptote is normally going to be y equals 0, but this minus 8 moves it down 8, so it would be y equals negative 8. Domain and range. So domain is the exact opposite of the vertical asymptote. So my domain is going to be everywhere but 2. So negative infinity to 2, along with 2 to infinity. I'm hoping this isn't writing too small for you to see in your video. Range is the exact opposite of horizontal asymptote. So range, and you don't have to write it in interval notation. I did for domain and range here. You can write it in different ways. I just prefer interval notation, but you can write it multiple ways. So range is anywhere but the horizontal asymptote, so it's everywhere but at negative 8. So we can write the range is from negative infinity to negative 8, along with negative 8 to positive infinity. And that's all information from transformations on the first slide. Okay, question 3. Identify any zeros and vertical asymptotes of f of x equals x squared minus 5x over x minus 2. Okay, so this is information from the second slide because this is definitely not 1 over x. So vertical asymptotes come from factors of the denominator, but I also need to check if any factors cancel. So I'm going to have to factor the numerator, x times x minus 5. Nothing cancels. So my vertical asymptote comes from factors of the denominator equal to 0. So x minus 2 equal to 0 would be x equals 2. So I have a vertical asymptote at x equals 2. And then I'm going to look for zeros. Zeros are when you make this equation equal to 0. And it looks like it would be terrible, but what actually works out easy is if I multiply both sides by x minus 2, well, it cancels here. That's still 0. So then you have x squared minus 5x equal to 0. And then I'm going to factor this. And from multiple chapters this year, if you have something factored equal to 0, you make each factor equal to 0 separate. So then I'm going to have x equal to 0 and x minus 5 equal to 0. So I would have zeros at x equals 0 and x equals 5. If you wanted to write them as points, because they're x-intercepts, you could write it as 0, 0, and 5, 0. It's kind of your choice. Okay, 4. Identify zeros and asymptotes of j of x equal to x minus 2 over x squared plus 6x. Well, immediately I'm going to factor the denominator because a lot of our information comes from that. Okay, so I don't know if I have any good order to do this. I guess I'll just do zeros since that's not affected by asymptotes. So I'm going to make my equation, oops, nice, let me erase that. X minus 2. I'm going to make this equal to 0, and when I multiply by the denominator, it goes away, and I have x minus 2 equal to 0, and that is just a single answer right away. So I have a 0 at x equals 2, which I could write as a point, 2, 0 if I wanted to. Now, asymptotes, vertical asymptotes, are factors of the denominator that don't cancel out. Well, nothing cancels on this question because x minus 2 is the top. So I set each factor equal to 0 separately and solve that. And I would have vertical asymptote at x equals 0 and x equals -6. I'm going to have a horizontal asymptote. Okay, so horizontal asymptotes, I need to look at the degree. The degree of the top is 1. The degree of the bottom is 2 because of the squared. Well, degree of the bottom is larger, so my horizontal asymptote is automatically y equals 0. Nice. Well, a lot of info up here so far. 5. Identify any holes in the function of k of x equal to x squared minus 5x plus 6 over x squared minus 4x plus 3. Holes specifically depend on you factoring, because a hole comes from factors canceling. So let me factor the top, which would be, let's see, minus 3 minus 2. And the bottom is going to be minus 3 minus 1. And it looks like I am going to cancel a factor because x minus 3 cancels. And since x minus 3 is the factor that canceled, then that tells me I'm going to have a hole, or I should write this. I'm going to have a hole at x equals 3. Boom. Excellent. Nice job. That was a lot of information. Feel good about yourself if you were able to follow that. Feel free to rewind, pause, whatever. That's the advantage of videos. Only one more section to go in 8.5. Nice.